Ionic strength, we just learned about it, and so that's where we discussed how does salts, how does their charge, how does the concentration affect analyte's concentration in solution. So today we're going to be looking at activity, and so activity is going to allow us to think about what's called an effective concentration, meaning instead of the concentration that you calculated when you were ignoring the effects of salts, what is the concentration of the species now that we know there's another salt present in solution that is going to affect those equilibrium properties. So it's going to shift it left or shift it right depending on what we know about a common ion or just a pure salt that does not have a common ion. So in looking at that, we're using something called activity. Activity is basically an expression of effective concentration. So instead of just what is the calculated concentration, if you ignore those effects of ions, what is the concentration, if you will, based on all the other things in solution that also affect your sample. So in this case, we're given activity. So activity is given the symbol. So AC is activity. Concentration of C, that's what's shown here in brackets, and then this symbol right here is your activity coefficient. So I define these terms over here, activity of C, concentration, and then activity coefficient. It's important to note that activity coefficient and activity, those are two different things. So this activity coefficient is what's used to change your concentration to make it so it's more of an effective concentration. So using this equation, this is your main equation. Let's look at this. So this is something we've always known about. So if you've got this equation where it's A goes plus B, you'll C and D, you've got your products and you've got your reactants. So when we're looking at an equilibrium expression, typically what you have seen is this one. This is the one you've always seen in general chemistry, and so this is the equation that we're now going to try and incorporate those effective concentrations instead of just the concentrations. This equilibrium expression is most commonly used, especially in general chemistry, but in actuality it should not be concentrations that are in here, but instead activities. And that's because we now know that equilibrium is affected by ionic strength. Why most people will assume that this is good enough is if your ionic strength is 1, or the closer it is to 1, the more it's going to behave ideally. So if there's nothing in your solution that's going to affect the ionic strength of the solution, then your compound, your analyte, is going to behave ideally and the equilibrium expression we learned before stands. But if there's some other ionic compound inside of the solution, it's going to change the ionic strength of your solution. And so then you need to incorporate activity. So this is the better expression for equilibrium, where instead of having concentration of C, you have activity of C. And it's still raised to the same power as it was in this expression. So these coefficients are still the exponents, and so we need to fix that, are still the exponents on your activities. And so it's activity of C raised to the C, activity of D raised to the D, activity of A raised to the A, activity of B raised to the B. Alright, so now let's keep going, because now we can substitute in, if these are all activities, that means we can substitute in the right-hand side of this expression into every A that we see here. And so in doing so, you're given now concentration times the activity coefficient, concentration times the activity coefficient, and so on. But each time you're raising it, both the concentration and the activity coefficient, to the power that correlates to the coefficient in the balanced chemical equation. So notice these are to the A's, these are to the B's. And so this is your new adjusted equilibrium expression that accounts for activities. If you don't have any kind of ions in your solution, so if your ionic strength is just 1, if it's unity, it's going to behave ideally, and in which case you can still use this expression. Alright, so then how do we use this? Where do we get this, or where do we get this? This is where your table comes in handy. So in class or on your D2L shelf, you should have this chart. So in this version of Harris, it was table 7-1, and the newest edition, it should be 8-1. So in this table, what you can do is you can look up the ionic strength is on the top, and you can look up the compound that you're studying. So in the left-hand side, it's the ion that you're studying, so your analyte, and then you scroll over. So if we're looking at hydrogen, we know hydrogen has a picometer size radius of 900, and then If your ionic strength is 0.001, then that means your activity coefficient is 0.967. Go ahead and check your table and make sure you understand that you're reading this table properly. So if you have hydrogen as your analyte and your ionic strength of your solution is 0.1, that means that your activity coefficient is 0.83. But now it sometimes gets a little tricky if, for instance, your value is not on the chart. So meaning, let's say my activity coefficient of hydrogen, my ionic strength of hydrogen is 0.075. 0.075 ionic strength is not on my chart. So if I had analyte was hydrogen and I'm measuring an ionic strength of 0.075, I can't just directly get it from the table. So what do? Do you give up? What do? This is where you can either interpolate or you can do the extended Debye Huckel equation. So let's learn how to do those. Let's try looking up an activity coefficient in the table. So to begin with, I want to ask the question, what is my activity coefficient for the hydrogen ion in a 0.072 molar sodium chloride solution? So the first thing you should do is you need to figure out ionic strength. That's why it's so important to know how to calculate ionic strengths. So if we were to do this for this equation, remember your mu is 1/2 times your concentration of sodium, in this case 0.072, times the charge of sodium. Remember, sodium is 1-to-1 with sodium chloride, same for chlorine. Your charge is going to be +1 squared plus, and you can really, the plus and the minus don't matter because it's squared, plus the the concentration of your chlorine times the charge of chlorine squared. If you do all that, ionic strength is equal to 0.072. Now, you look this up in your table and you find that it's not on there. So that means that we need to figure out what is it. So to begin with, what I like to do is I like to try and figure out what's it between. So what I mean by that is that we can interpolate or we can use this fancy equation and kind of plug and chug in order to figure out what my alpha is. Now something to be noted here, mu, our ionic strength, doesn't care what the solution is. So if it's 0.072 sodium chloride was what was in it, or 0.072 but maybe magnesium sulfate produced that, it doesn't matter. Ionic strength just tells you the net charge basically of the solution. So now that you've got this, and I need my units, molar. So now that I've got my units, let's look at the table. So option A for determining this is interpolation. In interpolation, what you're doing is you're taking a line. It's sort of like how you use a best fit line, so y equals mx plus b, how you use that equation to help you figure out, if I know these data points, what's the data point in the middle? That's all interpolation does. It's a way of using a linear pattern in order to figure out what number it could be if you know numbers on both sides. So in a way, it's a 2-point calibration curve. Now the problem with interpolation is that it's assuming a linear regression line. If it's not linear, this breaks down. And for this case, it's not exactly linear. So we'll do both just to practice and show you what it looks like, but you also should know that there are different pros and cons to each method. So interpolation, if we did that, we'd look up in our table and we'd see that our y's, or in this case our activity coefficients, versus our x's, our mu's. So if we look up an ionic strength of 0.5 in our table, of 0.072 and 0.10, we can look up and figure out what the correlating alpha is, with the exception of this one. This is my unknown y. And the reason I want to put both of these is you pick the data point below it and you pick the data point above it. All right, so now that we've got this table set up, what you're essentially going to do is you're going to do an unknown interval divided by a total change in y equals some known interval divided by a total change. Or another way I like to do this is A, B, C, and D, where I can then say A over B equals C over D. Let me slide over a bit so I have a little more room. So using this interval here, I can put my change here over the change here equals the little change over the big change. So in this case it is, and make sure you keep your orders right. So I'm going to go top to bottom top to bottom. So meaning 0.86 minus my unknown over 0.86 minus 0.83 equals my small interval 0.05, same order, keep the same order, over 0.72. All over my big interval 0.05 minus my final data point 10. And now I can do all this and I can solve for y. So to begin with, I have 0.86 minus y equals 0.0132, which means y, which equals my activity coefficient for hydrogen, that equals Alright, so we just found the first method, which is using the interpolation method. The method that allows us to look at the linear relationship between points around one data point and figuring out what that missing data point on the table is. The second way is, since we're looking at activity coefficients, there's the Debye Huckel equation, and so that is what you see here. So this equation here, log of alpha equals negative 0.51 z, remember z is charge, times, that's squared, times the square root of the ionic strength, over 1 plus this little guy right here, that is going to be equal to the ionic radius in picometers. So that can also be found on the table. So you can go look at your table and look down, and hydrogen's radius is going to be listed on the table, times the square root of your ionic strength divided by 305. And what happens is, while this assumed a linear relationship, this equation obviously does not. All right, so what you can do is just plug in all the numbers, calculate what the value is, and the reported answer at the end. So I encourage you to stop the video, try and plug these numbers in on your own using the table, and then see if you got the same thing I got. So what you should have gotten is your charge is 1, your ionic strength is 0.072, and that should be in both locations, and your radius is 900. So now you can do all the math. I like breaking it into 2 steps. So I often show log of gamma equals, in this case, negative 0.07637. And now I need to get rid of the log on both sides. So I raise 10 to both sides, which gives me an alpha equal to 87. All right, so now if we compare this to the alpha we got via the first method, this is very similar, right? But there is a difference. So the question is, which one's more accurate? I want you to think about that, okay? Hopefully you thought through, and this one assumes a linear relationship, this one does not. So just think about that, ponder it, and then in class we'll talk about what you think the real answer is.